record on the screen. Okay, we're going to get started on Module 3 this evening. And Module 3 starts a concept that is going to be new to us. There's going to be some things that we learned in Module 2 that we're going to bring over, especially things like components and rectangular component method. But we are now going to be applying this idea of equilibrium. So we'll be learning about that condition. As we look at our learning plan to get started here, you're going to notice I'll be using this PowerPoint to kind of guide us through, but we will be completing or looking at sections 2.3a, b, and c, okay, for this section. And then the problems that we're going to be working for practice problems are going to be the following sample problems. Sample problem 2.4, 2.5, and 2.6. This evening, my plan is to go over the first two, and then the next time we get together, we'll go over the third one as well as set up some homework problems, okay? And then we're going to have some application problems that we'll be handing in. So you'll notice that our practice problems are the 3 that we had just looked at. Again, 2 of them tonight, and the next time we get together, we'll do the last one. And then our application problems, you'll notice there are 5 problems here, okay? And these are down at the end of the chapter. Remember, they're in the kind of the middle of the chapter. So I have the page numbers listed here as well as the final answers that you should aspire to get once you're done with your problems. Okay, if not, I can help you with that. But I anticipate during our lab time the next time we'll probably get some of these things set up. Make sure you've got some good stuff to go on. Okay, so that's the plan. That's the plan. So let's go back to our learning plan, and I'm going to pull up the PowerPoint presentation, and we're going to use this to kind of guide through. Really, it's just one section, but there's multiple parts to the section. So the objective of this chapter, as we already started chapter 2 in module 2, and we took the first couple sections there. Now we're going to focus on this idea of equilibrium, but it's still going to be of concurrent force systems. And if you recall, a concurrent force system means that we share a common point with all of our forces. So we're going to now take those concurrent force systems and we're going to apply this idea of equilibrium. Now, we're still going to be working with vectors, so it doesn't hurt to just remind ourselves a couple of things about vectors. Number 1, a vector is fully defined by both magnitude and direction. And a vector is not just a line, it's a line with an arrowhead. So when you're identifying forces, which we're going to be working with, throughout, make sure that you always have an arrowhead, so that helps for us to determine what that direction is. Additionally to that arrowhead, we're also going to be adding angles when needed, okay? So as you can see here, you can see these forces have lines with arrowheads and then are labeled. Scalar quantities are going to be those quantities that only have one item you need to fully define them. So in contrast, things like mass, volume, temperature, we're not dealing with those, okay? Sometimes we use mass, and we'll look at that as we come upon it, but vectors is what we're interested in because those represent what a force is. Now, equilibrium of a particle is when all of the forces on that particle equals 0, okay? This class is called statics. So what that means is when our forces equal 0, we're not moving. Okay, now that doesn't mean we can't have equilibrium only when we're not moving. We can actually have dynamic equilibrium where we're moving at a constant rate. Okay, so if you've had physics already or have had a physics class in the past, you might have talked about that. All right, this is not that. All right, we are always going to be at rest, static, excuse me, in a static state. So that means that we are not moving. But the condition of equilibrium where all the forces equal 0 will be applied, okay? So it says here, if the resultant force, this is Newton's first law, the resultant force is 0, that particle or that body will remain at rest or will remain at a constant speed in a straight line. So it doesn't change your state of motion. And your state of motion can be one where you're not moving, okay? All right, equilibrium of a particle. As we look at this particular slide here, what I want you to notice is we have two forces, they share a point. Okay, so number one, that is a concurrent force system. Whenever we have two or more forces that share the same point, that doesn't mean that their point of application has to be the same point. Even if, for instance, if we move them along their line of action and they would intersect at a common point, that is still a concurrent force system. Okay, so we have a concurrent force system here, and you'll notice that they also have the same line of action. Okay, the same line of action. I just want to make sure everybody in the room is up here paying attention to Module 3 stuff, chapter 2.3, okay? Thank you. Because I want to be sure that you're catching this stuff. You might have other things in the class or other classes that you're working on, but please don't use my lecture time to do that. So I'll wait for everybody to be looking up here so I know that I have your attention. Greg, can I have your attention, please? Thank you. So you'll notice that we have these two forces. Even though one is going up and to the right 100 pounds, the other one is going down and to the left. They share what we call the same line of action. So that means that they're going on the same line, okay? Even though they're in different directions, line of action is the same. When we have forces on the same line of action, we can algebraically add them together once we assign a positive and or negative direction. So if we say that up in the right is positive, okay, and down on the left is and down and to the left is negative, notice that if I have a positive 100 and if I add to it a negative 100, what's the net result of that? 0. So that would mean I am in equilibrium right now because the forces add to 0. Okay, so this is a state of equilibrium at this point. Now, as I stated earlier, we're going to be dealing with concurrent force systems. So we are going to be seeing setups just like this on our practice problems as well as our application problems. But we can also add them graphically, as we see on the right-hand side. We are not going to be actively doing that or applying that in this class. But what I want you to notice is this, that when we do add things that are in equilibrium, okay, you're going to notice that we start at an origin with our first force, F1. We add F2, tip to tail, F3. And notice how F4 goes right back to the beginning. Because remember, equilibrium is a state where all the forces equal 0. There isn't anything left over when we add all those forces. Okay, we're right back to the beginning, if you would, graphically. But when I am adding and I'm applying, what we're going to find out in just a bit, the equations of equilibrium, we can do that in our, traditional concurrent force system where everything's coming from an origin. And then we're going to use the rectangular component method to solve these. And the reason we do that is because the two main equations that we're going to be using for equilibrium are some of the forces in the x equals 0. You see that down here. And some of the forces in the y equals 0. Remember in module 2 where we summed our forces in the x and we summed our forces in the y, and those were the x and y components of what would be a resultant, right? Here, we're going to do that very same process of summing forces in the y, but instead of, or x or y, but instead of setting that equal to a resultant x or y component, we're setting it equal to 0. Okay, and it's going to help us to solve for unknown quantities then in that equation of equilibrium. All right, so we'll be seeing parts of what we did in module 2. We're going to be building on that. So that's you're going to see some things that look familiar. Okay, so free body diagrams. Free body diagrams are going to be simplified versions of whatever the problem is that we're trying to solve. So in a problem, for instance, they might give you a situation like we see over here on the right, where we've got, a set of cables. We've got two people that are, kind of controlling the cables that are going over these pulleys, and they're trying to lift the load, it looks like, off of this truck, okay? So what we want to, a typical problem would be, what would be the tension in those cables, which would then translate not only from point A where these are coming together, but it would also let us know how much force the person would have to pull down with, and is that reasonable? Okay, that's really probably the question. So so solving problems like this, where we have a common point, we're going to find out. Then we can, solve for what the tensions in those cables would be based on the conditions that we have present. So drawing a simplified version of, meaning I'm not going to be drawing the cables all the way over the pulleys and showing all the detail of the truck and the load. We're going to be simplifying it down to just forces, okay, along their lines of action, which we're going to find tables kind of give us those lines of action, okay? So we will get practice on that. So here's an example of a simplified free body diagram where in that case, point A would have been connecting those three cables, if you would. And all we're going to do is reduce it down to what are the forces along each one of those cables to solve for those. And again, that helps us in a couple different ways. I'm going to go back over here. We might be interested in, okay, how much of a load can we lift with that so that we don't have too small or way oversized, cable or rope to actually lift that up. And then, like I said earlier, is it reasonable for humans to either pull down and be able to control that load? Okay. All right. So the first problem that we're going to be looking at here is going to be sample problem 2.4. Okay. And I have it underneath my paper here, but I think I'm going to go through it here because I can kind of got a nice clear picture that I can zoom in on. So the problem statement says in a ship unloading operation, a 3,500-pound automobile is supported by a cable. Okay. The rope is tied to the cable and pulled to center the automobile over its intended position. So you're going to notice here that we've got this cable. It's going over the top. So it's coming from A, going up to B, and probably secured somewhere, that we're not seeing. But you're also going to notice here that this person is pulling it, so maybe he's got to get it onto, a certain position on the ground there. So that person is going to be pulling it over. And we're given some information here. We've got 2 degrees from vertical. We've got 30 degrees from horizontal. They want to know what is the tension in the rope. Okay, and this is the rope coming over. All right. So what we are going to do is on page 41 is where this problem is. Okay. What we're going to do is we're going to go through the process of solving this problem, but we're going to do it a little bit differently than what the book is going to do. All right. The book is planning on doing it with a graph, kind of like that tip to tail method with the triangle. Okay. We're going to use our rectangular component method because then we can apply our standard equations of equilibrium, sum of the forces in the x and y equals 0. And we can then also use the component method that we started learning about the last time, okay, in module 2. So we're going to take just a slightly different approach, but we're going to be getting the very same answers that they have, okay? So first things first, I'm going to kind of get my paper out of the way here, and we are going to kind of get started with the diagram and such, okay? So this is sample problem 2.4. This is one of the practice problems you will be handing in, okay? So make sure that you're following along and you're performing it in the very same way that we're doing here because this is your formatting that you're also going to be applying in the application problems. Up in the upper right-hand corner here, we are going to be using what we call our convention, okay? Just like last time, we identified anything going vertically up was positive in the equations we were going to use, and then anything going to the right horizontally is going to be positive. Anything going down or to the left then would be negative, okay? Now, what we're going to be doing is we need to find, okay, the tension in cables AB and the tension in cable AC. Okay, and let's kind of look back where those are coming from our diagram. So if we look at the illustration here, A is right in the middle. Okay, that's going to be the origin, if you would, of our coordinate system. All right, then B goes up and to the left. All right, so this is going to be 2 degrees off of vertical, if you would. All right, And then we're going to have our 30 degrees going down to here. So C is down by the person that's pulling. So we want to know, what is the tension in cable A to B? And what is the tension in cable A to C? All right. Our automobile, remember, is 3,500 pounds. Okay. So we're going to be taking that into consideration. So we are going to start with a nice large coordinate system. Remember what I said last time? Half the page. Okay. I want it a third to a half the page for when you are drawing these things. We've got to put our vectors in place. And even sometimes when I think, oh, I've got a nice big diagram, I usually run out of room anyway. So I'm going to make mine really nice and big. So I'm literally taking, if you look at my paper, I'm taking a little bit even more than half the page. All right. So this large, if you're putting a little bitty thing, remember, the practice problems are 0 or 10 points. Okay. If you're not following the formatting or doing the things that I'm telling you to, then unfortunately, I can't give you 10 points. It's going to be 0. Okay. So make sure you're adding those in. All right. Now, this point right in the middle, now I'm not going to label it. This is point A. All right. Where everything comes together, where they all share that common point. That's point A. All right. That's going to be the center. The first thing we're going to draw, and this is going to be a force going straight down. This is going to be the weight of our automobile. So from point A on the cable going straight down, this is going to represent that automobile, and this is 3,500 pounds, okay? And we have to add our units. Remember, whenever we're showing our numbers here and we have any magnitudes, we want to put our units with them as well, okay? Then what we're going to do is we're going to add each one of the cables or ropes that are there. So the first one is going to be that cable going up to B. So I'm going to do the A to B. Now I'm going to put this as kind of a steep line, kind of close to that y-axis, because this angle right here, that's our 2 degrees. Okay, so even, I know mine is probably, I know it's bigger than 2 degrees, but we want to show it nice and close to our vertical. And this is going to be the tension AB. Tension AB. And then the other one that we have is going to be going down and to the right. This is going to be in that 4th quadrant. This is going to be a 30-degree angle from horizontal. Okay. And this is going to be tension AC. So all we did for this illustration is we are showing just the forces that are acting, with their common point being this origin, which is representing point A. And we are putting these forces along their lines of action, or in this case, along the cables that they would be on. Okay. Now, they are all pulling away from that origin because you'll notice that we're using the variable T. That means that there's tension in that cable. All right. So it's pulling, it's pulling on point A, pulling on point A, and pulling on point A. So each one of these are in tension. They also, this one has magnitude because the cable that is vertical coming from A, all of the weight of that car is coming off of it. So we know that one to be 3,500 pounds because it said that the car weighed 3,500 pounds. Okay, so the weight is going to be right along that cable. So that's what we have representing in that vertical direction. So any questions at the moment on why we did what we did? This is a free body diagram. Okay, so you can even say this is step number 1, FBD, free body diagram, step number 1. Okay, we always draw this out. Now, we are going to be applying our equations of equilibrium. All right, and I'm just thinking ahead. I'm not going to write this down, but I'm thinking ahead. Those two equations are sum the forces in the x equals 0 and sum the forces in the y equals 0. What do you think our next step is before we do those two equations? Break each one of the forces that does not lie on the x or y axis into their components, okay? So right now, our 3,500, we don't have to worry about. That one's done, right? But the two that we're interested in and the ones that we actually want to find, we need to do components for each one of those, okay? So our step number 2, if you would, is going to be components, okay? Now, when you are doing your work for me, okay, this is what I'm going to ask is that you work down the page. All right. Please do not like do a little over here, then do a little over here, then go over here. Even if you number things, it feels like you're trying to squish it all in. And it gets to be really hard for me to see what you're trying to do, especially when we're uploading them. So even if you have to go to a second page, it's okay. They make paper every single day. And actually we're keeping the paper mills in business. So please make sure that you're working down the page. Don't try to squish it all onto one piece of paper or one side of the paper. All right, so for our components, so let's draw our components on our illustration first. So go ahead and do that. And also add your labels. You should be pretty familiar from Module 2. Okay. So you'll have an X and a Y for each one. Now, again, you don't have to use a straight edge, but when you don't, your lines have to be straight. Okay, so you can sketch them if you're really good at freehand sketching. Otherwise, really easy to get a straight edge in there so that it represents it well and looks nice. Okay. Once we have all of our X and Y's drawn and labeled, we're now going to calculate them down below. Okay, so I'm going to start with the tension in AB. So tension in AB, and this is going to be the X component, is going to be equal to, all right, if I look, this X component is right here, right? Now, my 2 degrees that is given to me is this angle right here. And my TABX would be the equivalent length on top here, right? Okay, if I look at it this as a right triangle. So if I want to find TABX, it would be the side opposite from the 2 degrees. And then we want to put it in terms of its hypotenuse. So that means we're going to be using the sine of 2 degrees, right? Multiplied by the hypotenuse TAB. Okay. You guys see that form there? So when we show the sine of an angle, we usually say sine of 2 degrees is equal to the side opposite over the hypotenuse. But instead of writing that first step, do you guys feel like you can make this leap right here where we put the length of the component? If you want to do it in 2 steps, that's fine. But if you want to start here, that's good too. I believe you're trig experts at this point. Okay. So now you'll notice that we don't have a magnitude for the length of that hypotenuse, right? So what we're going to do here is we're going to put it in terms of the hypotenuse. So all we want to do is the part that we can go a little further with is what is the decimal equivalent of 2 sine, and that is going to be TABX is equal to 0.0349, right? Do you kind of like that? 4 decimals, TAB. So this will be where we stop with it because we can't solve. There's 2 unknowns here, right? Okay. Now let's look at the Y component. All right, so if we look at the y component here, we look where our 2 degrees is. The y component is going straight up. That is a side adjacent. And then we're going to put it in terms of its hypotenuse. So this would be TABY is equal to the cosine of 2 degrees times TAB, the hypotenuse. So TABY, find the decimal equivalent of 2 cosine, that's going to be 0.9994 because it would be 39 is the next. And then TAB. Do not put 1 here, all right? Hold in the problems when you're doing these, hold at least 4, 5 decimal places, okay? Because we don't want to round too much too early because then our numbers can be way off. So make sure this one is 0.9994 TAB. Okay. All right. Questions? Jaden. Oh, so for instance, either one of these, I'll do the cosine. So if you say cosine of 2 degrees is equal to the side opposite TABY over TAB. Rather than writing out this step, you could if you want to, but I'm going right to rearranging, multiplying the TAB up. Okay, so this is going to be TAB. And then I just start with TABY is equal to the cosine of 2 degrees. So I'm putting this right here right away. Does that make sense? You may have done that in your math classes before, kind of that little, I don't know if it's a shortcut. It's just a quick rearrangement. If you want to start here, go right ahead. I'm just saving a line. That's all. All right. Any other questions? Okay. So then we've got one more force to do here, right? We've got to do the X and Y components for our TAC. All right. This time our 30 degrees is in this position. So if I want to do my TACX, that is going to be this time the side adjacent to our 30 degrees in terms of its hypotenuse. So this is going to be the cosine of 30 degrees times TAC. 30 cosine, what do we get for a decimal equivalent? I'm going to pull the chat box from our virtuals because they might want to chime in, and feel free to do so. What do we get for the decimal equivalent of 30 cosine? Anyone? 0.866, yep. And then it's like 0.25, so that should be good. 0.866, and that's going to be TAC. Oh, thank you, Matthew. I see you got it. Yep, so this one we're going to keep in that very same form. Okay, can't really get an actual number because we don't know the magnitude of TAC, but we'll be able to get that soon. And then we're going to do the TACY. Now up here, you'll notice that the Y would be the equivalent side opposite. So this will be the sine of 30 degrees, right? Times TAC. What is the decimal equivalent of 30 sine? 0.5, perfect. I'm seeing them on virtually, great. So 0.5, and that is even, like it's just 0.5 and then 0, 0, zeros, right? And that's going to be TAC. There we go. Great. So as we look at our diagram then, you will notice that we now have all of our forces on the X and Y axis now. All right. Now what this allows us to do is to use those 2 equations of equilibrium and focus on the verticals and the horizontals. Okay. All right. So step number 3 is going to be equations of equilibrium. Okay. Now we're gonna get one more equation of equilibrium, but the 2 that we're going to be using here are going to be those sum of the forces in the X equals 0 and sum of the forces in the Y equals 0. And all that means is just like in module 2, we're going to focus on horizontal and vertical axis forces in each one of those equations. All right. So we're going to start for no other reason than I don't know, we always say X before Y, right? We're going to start with the sum of the forces in the X equals 0. Now, you have to write this equation for me. Whenever you are summing your forces in the X equals 0, bless you. It's like you're announcing what you're doing. I like to say this is the equation in variable form, if you would, okay? And before you do anything, you have to write this out. Now, this is an equation of equilibrium. You're going to hear me say this over and over again. It needs to have an equal sign and it needs to have two sides. Okay? If in any line that you write below here doesn't have an equal sign and two sides, points off. I'm so sorry, but it has to. All right? We don't want to magically appear at the end. All right? So, sum of the forces in the X. That means that we're going to go up here. And we're going to look only forces that lie on the x-axis. This is why we don't float forces. I don't want to see any diagrams with x's up here. I don't want to see any y's out here because we got to look what is on the x-axis. That's why the x components have to be on the x-axis. You might be like, yeah, no, duh, Kelly, but you will be surprised what I get to see. And I think in math classes, they allow you to do that to visualize where the force is. But in actuality, the forces are on the axes. So make sure you draw them there. Don't float them for me, okay? So you should see two forces on your x-axis. All right. Now we're gonna reference our convention. Anything that is going to the right will be positive in our equation. Anything going to the left will be negative. Okay. So you'll notice that we have a positive ACX, right? Or TACX, and we have a negative TABX. So we're going to write that first. So we're going to say, okay, positive TACX minus TABX. Now, if we go back up and we look, those are the only two forces on the x-axis. If we've exhausted those, then that completes the left side of our equation. That's the sum of the forces in the x. And now we have to set this equal to 0. Don't forget that. I'm looking for that. All right, now what we're going to do is directly down below it, just like we did in Module 2, we're going to look up here. We're going to say, oh, I have some equivalent values here of TACX and TABX. So I'm going to put their terms in terms of each one of those in terms of their hypotenuse. So for TACX, it's going to be 0.866 TAC minus for TABX, it's going to be 0.349. I'm sorry, 0.0349 TAB, right? Equal to 0 once we have both of those in place. Okay. Now what you're going to notice is that we have two unknowns here. Algebraically, we can't solve this. This is as far as we can go. So we're just gonna leave it in this form for right now. All right. And we're gonna be like, oh, no worries. We've got another equation of equilibrium that we can use and we can see how we do there. Okay. So I'm gonna go on my next page. I am not gonna try to squeeze this in at the bottom. Okay. That's not what I'm gonna do. And you're not gonna do that either. I'm gonna go to the next page, start fresh. You're gonna say, oh, this is still part of my step number 3, equations of equilibrium. But this time now, I'm going to sum my forces in the y equal to 0. Again, you have to tell me what you're going to do before you do it. So we're going to go back to our illustration here. Actually, that's what I'm going to do. I'm going to put this underneath here. And I'm going to look only on the vertical axis. Okay, go ahead and write out what you think the sum of the forces in the y are using the variables that are on our vertical axis. Don't shout it out yet. We'll look at it together in just a bit. And then you can compare. All right, let's compare. I'm going to write mine out here. So I'm going to start with the TABY. That is going up according to my convention. That means that that's positive. So I'm going to have a TABY. Then I've got a negative TACY because it's going down. And then I also have a negative 3,500. And make sure that you put the units of pounds, whether it's LB or the symbol, you have to have that as part of the 3,500. So this takes care of my sum of my forces in the Y because I just have three forces on the Y axis. Okay. If you'll notice here, there are two forces on the y-axis. Yes, they would be on top of each other, but I like to show it just slightly off a little bit just so I can recognize and easily see there's an extra force there. Okay. You don't have to do that, but just make whatever force, if they're one over the top of each other, that you can see that there's more than one force there. So now I'm going to set this equal to 0. All right. Now, each one of these values, if you recall, we have them in terms of their hypotenuse. So directly below each one here, I want to now just put them in terms of their hypotenuse. So ABY is 0.9994 TAB minus TACY is going to be 0.5 TAC. Now, the minus 3,500, I'm just going to push to the other side right away. All right, so I'm going to say equal to a positive 3,500. Do you see what I did there? I just put it over instead of setting it equal to 0. Now, I still have two unknowns here. So unfortunately, I can't go any further. Okay. But. Step number 4. Okay. Step number 4. We are going to notice that we have two equations with the same two unknowns. So we can do the substitution method. Okay. And we all remember that, right? Module 1. So if we look over here, the first equation we have is this one right here. We could call this number 1. Okay. So our equation number 1, and I want to see these labeled. All right. So don't just start doing work. All right. I want to see which is your equation number 1, which is your equation number 2. So again, the way that I'm doing this is how I want to see you write it out. So equation number 1 is going to be 0.866 TAC minus 0.0349 TAB equal to 0. So this is equation number 1. All right. Two unknowns, TAC and TAB. Equation number 2, immediately below it, 0.9994 TAB minus 0.5 TAC is equal to 3,500 pounds. Okay. So these are the two equations that I'm going to be dealing with. Notice they are two equations with the same two unknowns, right? And here again, chronologically, vertically below or horizontal lines below, we're going to then do this step by step, okay? As we look at these two, we're going to use that substitution method. We need to get one of the variables in terms of the other. And we have to choose which equation do I want to deal with. Sometimes one might look easier to deal with than the other. And it can be a horse or piece, either one. I don't think either one of these is easier than the other, but number 1 has a 0. So that's usually just kind of easier to deal with. So I'm going to go with number 1 is where I'm going to start the substitution. So using equation number 1, okay, 0.866 TAC, I'm going to push the TAB to the other side right away, is equal to 0.349 TAB, okay, to eliminate that 0. And now I want to get one of the variables by themselves. Whether it's TAB or TAC does not matter. I'm going to pick TAC because I like to have my unknown variable on the left side. That's it. Okay. If you're like, I want to do TAB, go ahead. All right. That's totally fine. But I'm going to solve for TAC here. So I'm going to divide both sides by 0.866. And I'm going to get TAC equal to.
You need a 0, Kelly.
What was that? Oh, I
The
need a zero here, don't I?
yeah, yeah.
Thank you, thank you, thank you. Point, there we go. Thank you. 0.0349. Yes. Talking and writing. So what does TAC equal? Looks like Matthew got 0.0403. That's what I got too. TAB. Okay. Now, I started with equation number one. So now I'm going to go to equation number two, now that I got TAC in this form. So now wherever I see TAC in that second equation, I'm not going to write TAC. I'm going to write 0.0403 TAB. So equation number two, okay, because you got to kind of alternate. I like to think alternate back and forth between the equations. 0.9994 TAB minus 0.5. This is where I'm going to put, instead of TAC, 0.0403 TAB. Okay, because that's what TAC is equal to. So I've got TAC in terms of TAB, and now I use that right down here. Okay, is going to be equal to 3,500 pounds, right? So now I need to distribute that 0.5 here. So I'm going to have 0.9994 TAB minus point zero two TAB, I think. I'm looking at my notes. I better double check. Yeah, because it's 0.02015 is equal to 3,500 pounds. So now we can combine these two. And then solve for TAB. Now, this is one of the final answers that we need. The tension in cable AB should be 3,574 pounds. Okay. Notice you have 3,500 pounds. You're going to divide by a unitless decimal. So the pounds stays. Okay. Did everybody get that value? It looks like Matthew, you got the same thing as me. Good. And then a box around this, because again, this is one of our final answers. When you put a box around the final answer, remember, it asked for in our problem, what is the tension in cable AB, right? So your final answer needs to have TAB, the tension in cable AB is equal to, here's my number with the units, all right? Do not just circle 3,574 pounds. I don't know what that's equal to. And then you might say, well, up here I was calculating. I don't care. Final answer needs to be TAB is equal to, okay? Make sure you put that in. All right. And now that we have TAB, we can substitute it back into, since we used it to equation number two to solve for it, we have to put it into equation number one. Now, we can put it back up into here because this was equation number one rearranged. So going back to equation number one, TAC is equal to 0.0403 times, that's our TAB. It's going to be 3,574 pounds, right? Does that make sense, everybody? We're substituting in the actual value where TAB was. So now our TAC should be 144.03 pounds, or 144, I think is a good number. Okay. Box around that with your label of your variable equal to, and then make sure that your units are in there as well. So let's review the process, okay? First thing that we did on our problem is we drew a good free body diagram representing the problem, okay? In this case, we had two unknown forces going along cables, tension in cable AB, tension in cable AC. We had the angles given in our problem, and we needed to find those values based on the fact they were lifting a car that had a weight, which is an arrow or a vector representing that weight going down to the center of the earth, if you would. And that's going to be 3,500 pounds. We broke each one of the forces that were not on the X and Y axis into their X and Y components, knowing we were going to use our two equations of equilibrium, some of the forces in the X equals 0, some of the forces in the Y equals 0. So we had to have everything on the X and Y axis. So components were next. All right. Then we used those equations of equilibrium to get our equations as far as we could. And in this case, we ended up with two unknowns, TAB and TAC for our first sum of the forces in the X equals 0. Now, when you do your equations of equilibrium, you have to tell me what you're going to do. Sum the forces in the X equals 0. Remember, this is an equation of equilibrium with an equal sign and two sides. The left side in this case is going to be summing our forces in the X, looking at that X axis, what forces are on there, comparing them to the convention that we assigned, and then giving them the proper X or positive and negative value. Because we couldn't solve it, there was too many unknowns. We then went to our second equation of equilibrium, sum the forces in the Y equals 0. We looked at that vertical axis and we had three forces here, a positive TABY, a negative TACY, and a negative 3,500 based on our convention. We solved as far as we could, but we ended up with two unknowns, TAB and TAC. They were the same two unknowns as our first equation, so then we could use two equations, two unknowns substitution method to solve for those two variables. Okay? So any questions on the process? Bits and pieces of this we used in Module 2. We learned that rectangular coordinate method of solving, or rectangular component method of solving these problems. So we use those rectangular components up here. The new thing was summing our forces in the X equal to 0, saying that this was an equilibrium, okay? That the forces, we were in a balanced, steady state, okay? And by applying that, we could then determine what were the values in the forces that we needed to find, or the tensions in those cables, okay? All right, if there aren't any questions, then what I'm going to do is I'm going to stop the recording here.